Hello, I'm Hugh Manfield, and welcome back to the lecture series on fluid space theory. Now, at any time during the lectures, if you want to know more, you can pick up a copy of my book, Einstein and Aliens, A New Approach to General Relativity. It's available on Amazon.com, and it has all the math worked out in the appendices in detail, so you can look there as a reference. Today, we're going to be talking about Newton's laws and reference frames. And this is the last lecture preparing before we can go directly into what fluid space theory is and how it works. So by the end of this lecture, you should understand how Newton's laws are actually, they're called Newton's laws of motion, but in my opinion, they're actually Newton's laws of space. So, Newton gave us 3 laws of motion, and they're still in use today, and they totally changed the world. Every mechanical device, from airplanes to ships, automobiles, are basically derived from Newton's laws. So what are the laws? Basically, an object in motion will remain in motion until acted on by an external force. An object at rest will remain at rest until acted on by an external force. The second law, the change in motion of an object acted on by an external force is directly proportional to the magnitude of the force and inversely proportional to the mass of the object. So what does that mean? You can write the equations in math. Here it is straight from the law. Acceleration equals force divided by mass, or a better, more useful form is force equals mass times acceleration. And the third law is for every action there is an equal and opposite reaction. So to use these laws and apply them in fluid space theory, I recast them in terms of the reference frames and how the object is related to the reference frame. So, the new first law of fluid space theory is that objects move through space without resistance. And conversely, space can move through an object without resistance. So, if you set an object into motion, it will stay in motion forever out in space, traveling at a constant velocity in a straight line, and it will never stop. So that means zero friction. It moves through space without resistance. And an object at rest will remain at rest. Basically, there's no real defined reference frame. It's just that if you define the reference frame that is co-moving with the object, then that object is at rest with respect to that reference frame. And to change it with respect to that reference frame, you have to act on the object with a force. And that brings us to the fluid space theory second law. An object acted on by an external force will change its state of motion with respect to its resting inertial reference frame in direct proportion to the magnitude of the force and inverse proportion to the mass of the object. So that really gives us the same equations as from Newton's laws, force equals mass times acceleration. And the third law of fluid space theory is that in order to change the relationship of an object with its resting reference frame, the acting object must change its relationship with its own resting inertial reference frame in equal proportion. It's the same basic law, but it's cast in terms of the object in relationship to their inertial reference frame. So, looking at the first law, we would have Ricky in the box floating free, and she's been there for a while, so everything is settled down, nothing is moving, all the objects are at rest with respect to the box. And they will remain that way forever until some force comes along and causes the box to move. And then they will begin to change their relationship. So in the first frame, the first law of motion is in effect. And in the second frame, when we apply the force to the box, now everything in the box is behaving according to the second law of motion, except for Stan. He's still floating free, obeying the first law of motion. So the second law of motion shows how objects will change their velocity because they've been acted on by a force. So we have the rocket-powered football field. the motors are on. So everything on board the field is going to be obeying the second law of motion. And you will feel gravity on board. There's a force, and you're accelerating from that force. Now, before we turned the rockets on, we launched the football, and it moved, according to Newton's first law, in a constant direction at a constant velocity. As soon as we turned on the rockets, from the point of view of the field, the ball began to curve. So if you were standing on the field, you might look up and think, there's a force acting on that ball to bring it down to the earth. And you would imagine that's the force of gravity, just as we do when we're standing on the earth. But that is actually a useful fiction. There's no force acting on the ball. It's still continuing to obey Newton's first law, traveling at a constant velocity in a straight line, and the field is catching up to it. The field is accelerating upward through space, catches up to the ball. There's no force actually acting on the ball, but from the point of view of the field, you see the ball move in a curve. And this is important to understand about gravity and how fluid space theory works. And the third law of motion is pretty simple. If Stan is floating in space, ready to throw the ball, as soon as he throws the ball, if the ball moves off at a high velocity, Stan has to move back at some other velocity in equal proportion. So that if the mass of the ball is smaller than Stan, the velocity will be higher. The mass of Stan is higher than the ball, then his velocity will be lower, but the momentum is conserved. The small mass times the high velocity must equal the large mass times the lower velocity. So now let's think a little bit more about reference frames and forces acting on them. In this case, we have the football in a box. Now, there's something special about this box. It's a magic imaginary box that is actually stitched to the fabric of space-time. So if we move the box, it moves the reference frame of the ball with it. And this is something that's been referred to in physics as frame dragging. If I can move that box with the reference frame, I can drag the box and all of its contents along with it. I'm moving the entire reference frame. And what does that mean? That means the ball will stay at the same coordinate that it is within that reference frame unless it's acted on by a force. So if we don't act on it with a force, then if I move this box, the ball and anything else in the box will come along for the ride for free. No force required. If we were actually moving the fabric of space. So I don't know if you've seen the movie Men in Black. It's an old movie, but spoiler alert, the galaxy was on the collar of the cat. Now, you may wonder, how could a cat carry around a galaxy on its collar? Well, if you could put a magic box around that galaxy that moved the reference frame of the galaxy, and then you could somehow scale that down to fit on the cat, then the cat would actually have no problem carrying the galaxy around because you're not actually moving the galaxy with respect to its reference frame. So you can move a galaxy quite easily with just a push of a finger. So this would indeed be a godlike power. If we could grab the fabric of space-time and actually move it, we could move stars, planets, solar systems, whatever we wanted. But to actually grab the fabric of space is a pretty tricky thing, and I'm not sure there's actually a way that we can do it. So, if we want to understand gravity in terms of reference frames, what we have, Ricky is floating free in the box, feeling weightlessness. So she's in an inertial reference frame. Stan is going to feel gravity because we're applying a force to his suit, so he's going to be hanging in his suit, and he's going to see the ball and the box and Ricky all fall past. So we're actually dragging Stan away from the inertial reference frame. So this is kind of a poor man's version of frame dragging. Stan is being dragged away from the reference frame, so he sees the inertial reference frame falling away. So we bring that to the surface of a planet. Now we have forces acting on the bottom of Stan's feet. He's still being dragged away from the inertial reference frame, and he sees the inertial reference frame falling toward the surface of the planet. So this is what's actually going on with gravity. But there's a problem, and it sounds like an impossible problem to solve. If that's true, the Earth has to be like a giant space-time vacuum cleaner sucking up space falling through the entire surface at all times. So how can that happen? Well, it's one of the best kept secrets of the cosmos, and it's a problem that no one else is going to think of without fluid space theory. And that's what I'll show in the next lecture, is how this actually works. So now that you know how Newton's laws of motion are actually laws of space, you're ready to learn the secret of fluid space theory, how the Earth can be a giant space-time vacuum cleaner. And if you haven't already subscribed, please subscribe and check out the link below for the playlist. Until next time, keep learning science. I'm Hugh Manfield.